A Pelton wheel is an impulse turbine for turning the kinetic energy in a jet of water into rotational energy on a shaft that can be used to generate electricity or do other work. What happens is a wheel like this with multiple blades on it interacts with the jet of water so that the buckets, as they swing up, they'll swing into the jet, catch the jet. The jet will exert a force on the bucket, turning the wheel. Now, as these buckets swing up, one of them will be interacting with the jet, this one's just about to come up into the jet. This one's been in the jet for a while, and there's water here that's still coming from the jet and hitting this bucket that had passed by that bucket before it swung up into the jet. So the water's typically hitting more than one bucket at a time. Now, if we look down from above, the buckets look something like this. The jet hits them and is turned around almost 180 degrees so that the fluid goes off, the water goes off in the other direction. We can do an analysis by approximating the motion as linear with the velocity of the bucket. This bucket's moving at a velocity that depends on the rotational velocity, the omega rotational velocity, and the distance out from the center of rotation, so omega r. Now, if we want to do some analysis on this, we need to work with the bucket stationary in our frame of reference. So we'll use a frame of reference that's moving in this direction with the bucket. If we look at that moving frame of reference, then the bucket will be stationary. The jet is approaching the bucket a little more slowly than the original nozzle velocity from the nozzle that created the jet over here. And we can calculate the force. So first off, we use Bernoulli's equation. Bernoulli's equation tells us that if the bucket's not moving, there's no energy loss to the fluid as it passes through here, again if we neglect friction. And as a result, V1 is equal to V2. Capital V's, because these are total velocities, not the lowercase v that's the y component of velocity. So the velocity coming in here and the velocity going out there are the same. And the velocity coming in here is the nozzle velocity minus the velocity of the blade. If the blade was moving away at the same velocity as the water coming out of the nozzle, then the relative velocity would be 0. So it's the nozzle velocity minus the velocity at which the blade is moving away from the fluid coming out of the nozzle. Continuity tells us that the steady flow, mass flow coming in, mass flow going out will be the same. So m dot 1 is equal to m dot 2. And both of those depend on how quickly the fluid's coming in here. So although there may be a larger mass flow coming out of the nozzle, because this bucket is moving away, the mass flows in only at the relative velocity across the control volume boundary here. So the mass flow will be the density times the velocity times the cross-sectional area. Velocity at 1, cross-sectional area at 1. Now that will be equal to density. It's incompressible, so the same density throughout. V1 is V nozzle minus V blade. A1, same geometry of the jet here as it was up there, so still the same area as the nozzle. So the force acting on this single blade in the acting on the fluid in the x direction from this single blade, from a momentum balance, there's no pressure forces, no other forces other than the force of the blade acting on the water, m dot times u, the component in the x direction, out minus m dot times u, the component in the x direction, going in. Now that'll be rho v1 a1, that's the m dot coming in here at location 1, times, and it's the same as the mass flow going out at location 2, times the velocity in the x direction of the flow going out. So if this is the positive x direction, as usual, going from left to right, then this x velocity will be negative v2, the magnitude of the velocity going out here, the absolute velocity. Minus m dot, again, is rho v1 a1 times the velocity in the x direction coming in here is just v1. So that's the x velocity coming in. Now both v1 and v2 are equal to vn minus vb. a1 is an, the nozzle velocity, or sorry, the nozzle cross-sectional area. And if we combine those together, we wind up with negative 2 times rho times the area of the nozzle times the incoming velocity, Vn minus Vb, the relative velocity overall, squared. And that's the force acting on the fluid. So it's negative. Or Fx equals 2 rho An Vn minus Vb squared on a single blade. Now remember, up here sometimes this jet is hitting more than one blade at a time. For a single blade, we see only this force. But sometimes there's a force acting on that blade and a force acting on that blade. So that the mass flow that's having an effect on the combination of blades is the overall mass flow. So all of the mass flow from the nozzle hits some blade, one of the blades on the outside of the wheel. So as a result, the sum of the forces on all of the blades will be equal to 2 times rho times V normal, A normal, or V nozzle, A nozzle, the mass flow coming from the nozzle, times the velocity of the nozzle minus the velocity of the blade. So this is the mass flow of interest, this is the velocity change of interest. And that's on multiple blades. Typically we might expect two blades in contact with the jet of water at the same time. So if we look at this force acting on those blades, then for increasing values of the blade velocity, the force goes from a maximum, if the blade's not moving, down to a minimum of 0 if the blade is moving at the same speed as the nozzle velocity. And it goes linearly down like this. So that's the force acting on the blades. At the same time, the blade velocity is going up like that. And the power delivered to the blades is equal to the force acting on the blades times the velocity at which those blades are traveling. That'll be equal to 2 rho A nozzle times V nozzle V blade minus V blade squared. And that will be a parabola that goes up, has a maximum right there in the middle, and then comes back down again. So there's no power delivered to the blade if the blade is freewheeling at the same speed as the nozzle. If the blades are just whizzing by at the same speed as the water coming out of the nozzle, the water doesn't do any work on them. It's just pinwheeling and spinning around like that. On the other hand, if the blades are locked still, the water doesn't do any work on the blades because there's no motion. Right in the middle is where we get the maximum power output from our blades. Now this makes sense because what's happening if the wheel is moving at exactly half the speed of the nozzle? Well, stuff will be coming in here at 1/2 of the nozzle velocity. It'll be coming back out of there at 1/2 of the nozzle velocity relative to the bucket. But the bucket's traveling this way at half the nozzle velocity, so the fluid that comes out of here in our larger frame of reference is coming out at a velocity of 0. So as a result, we've taken all of the kinetic energy that we had in this jet and turned it into rotational energy driving this wheel. The fluid that comes out here at location 2, once we translate back into our larger frame of reference, has no kinetic energy. All of its energy's been transferred to the wheel. As a result, it's just sitting still in space when it comes out of this bucket here. What happens then? The next bucket to come along smacks right into it. So obviously that won't work. We need to get this fluid out of there. So in practice, instead of turning through 180 degrees, these buckets will turn through an angle just a little bit less than 180 degrees so that the fluid will go off to the water will go off to the side here. And it will go out with a velocity just a little bit bigger than 0 so that it'll actually clear out the sides of the bucket. But the result is that we still get power very close to this maximum theoretical power, and it still happens at very close to 1/2 the nozzle velocity for our bucket velocity. Pelton wheels like this can achieve efficiencies in terms of shaft power output on the order of 95% or more, so they're very, very efficient devices.